What do Galileo Galilei and modern astronomers have in common? An instrument that decodes the sky, the refractor. But why is this telescope still the favorite tool for observing the sky after centuries? Stay tuned, you'll be surprised.
Refractors, also known as refracting telescopes, are the oldest and simplest type of telescope. Refracting telescopes have a long history. Galileo Galilei used a simple refracting telescope to discover Jupiter's moons and lunar craters. Today, refractors are still the first choice for precise observations, especially in planetary science.
In the next chapter, we will take a closer look at how a refracting telescope works and why it is so easy to use.
A refractor uses one or more lenses to refract light and concentrate it in a focal point. Light from celestial objects enters the tube through the objective lens at the front of the tube. This lens concentrates the light rays into a common focal point, also known as the focus, where a real, laterally reversed image of the observed object is created. This image is viewed through the eyepiece at the rear end of the tube and magnified to make it visible to the eye. This design makes a refractor easy to understand and intuitive to use.
How does focal length affect the performance of a telescope? We will answer this important question in the next chapter.
As well as providing stability, the tube protects the optical elements from dust, moisture, and stray light, ensuring a bright, high-contrast image. The distance between the objective lens and the focal point, known as the focal length, determines the magnification and field of view of the telescope. The eyepiece can be changed depending on the desired magnification to adapt the view to different celestial objects. A focuser is used for fine adjustment of the image, which precisely adjusts the eyepiece to provide a sharp image.
How do you ensure a stable and accurate mount for a telescope? The answer is in the next section.
The entire telescope is mounted on a tripod. This sophisticated and robust design makes refractors particularly suitable for beginners and ideal for observing the moon, planets, and binary stars. They offer intuitive operation, maintenance-free optics, and excellent image quality for many astronomical applications.
But what about possible image errors? We'll get to that next.
Early refractors often had a color error known as chromatic aberration. This occurs because light of different wavelengths is refracted to different degrees as it passes through a lens. Blue light is refracted more than red light, so the colors do not converge at a common focal point. This results in blurred images and color fringing around bright objects, which affects contrast and image quality.
However, chromatic aberration can be corrected. Special lens designs have been developed to minimize chromatic aberration. These are known as achromatic and apochromats lenses. The difference between these designs is explained below.
An achromat consists of two lenses, usually of crown and flint glass, which are differently shaped and combined. Due to the different refractive indices and dispersion properties of these glasses, two colors, usually red and blue, are brought together in a common focal point. This results in sharper images with less color fringing, but the correction is not complete and residual errors may remain. Main features of an achromat. An achromat consists of at least two lenses with different types of glass to minimize chromatic aberration. Dual wavelength focusing corrects chromatic aberration by bringing two specific wavelengths of light, usually red and blue, together at a common focal point, reducing color, fringing at high contrast edges, and resulting in sharper images with more detail. Unfortunately, an achromat cannot completely eliminate chromatic aberration. Small residual errors in the form of color fringing may remain visible. This design is a more cost-effective alternative to apochromatic lenses, which offer even better color correction. An apochromat goes one step further and uses a high-quality lens system with 3 or more lenses made of special glass. The chromatic aberration is almost completely corrected by precisely focusing 3 or more wavelengths of light. As a result, at least 3 colors are combined in one focal point, almost completely eliminating chromatic aberration. Apochromatic refractors therefore provide extremely sharp, high contrast, and true color images and are ideal for demanding applications. Key features of an apochromat. By focusing 3 or more wavelengths of light, the highest color correction is achieved, and chromatic aberration is almost perfectly minimized. Images are razor sharp, rich in detail and contrast. Brilliant, true-to-life colors ensure unsurpassed picture quality. The sophisticated design uses high-quality special glass with 3 or more lenses. This design is ideal for demanding applications such as astrophotography. In the premium segment, this lens design offers the best possible optical performance.
What are the special advantages that make spotting scopes so popular? Their strengths go far beyond ease of use. Find out more in the next section.
The choice between an achromat and an apochromat depends on individual requirements and budget. Apochromats are particularly suitable for applications where the highest color fidelity and image quality are required, such as astrophotography. For visual observations on a moderate budget, achromats can provide satisfactory performance. Refractors provide particularly high contrast images due to their closed tube and optical precision. This makes them ideal for observing planets, the moon, and binary stars. Beginners in particular will appreciate the clarity and detail of the images. Unlike reflector telescopes, refractors do not require regular adjustment. The objective lens is fixed and largely protected from dust and dirt by the tube. This makes them extremely low maintenance and durable. Refractors are often compact and light. They are quick to set up and ready to use. Cheap refractors can produce a rainbow effect around bright objects. High-quality refractors with apochromatic lenses minimize this effect. As lenses get heavier with increasing size, refractors are usually limited to smaller apertures. This limits their light-gathering power and therefore the observation of faint deep sky objects.
You have now learned a lot about refractors and their characteristics. Let's take another look at the main points.
Refractors are particularly good for observing the solar system. If you want to see sharp details on the moon or the bands and moons of Jupiter, a refractor is an excellent choice. Double stars, where fine detail is important, can also be studied very well. However, they are less suitable for faint deep sky objects. Refractors offer a combination of ease of use, robust construction, and excellent image quality. They are suitable for novice lunar and planetary observers, as well as experienced astronomers who appreciate high contrast and fine detail.
Thanks for watching this video. I hope you enjoyed it and learned something new about refracting telescopes. If you liked the video, I'd love for you to subscribe. That way you won't miss any more exciting content. And let me know in the comments what topics you're particularly interested in. I'd love to hear your ideas. See you next time, and a clear view of the stars.